Alright, this is 15.8. This is the final chapter of the text. This is on the divergence theorem, which is also known as Gauss's theorem. It's worth knowing that because if you look at some old final exams, they'll say for some problems use Gauss's theorem, so it's just the same as the divergence theorem. So the divergence theorem is basically another connection between integrals, but specifically it deals with surface integrals of vector fields. So I'm just going to give a specific, I'll give the theorem, make a couple of notes, and just do a couple of examples. And then I'll do some more notes as we go through the examples, because the divergence theorem can lead to sort of some interesting, fun problems, or easy to do problems if you like. So this says the following. It says, suppose sigma is a surface which completely surrounds a solid D. So what you want to think about here is that D is the solid and sigma, this is going to sound repetitive, but D is a solid and sigma is its surface. So maybe think of D first. Maybe a better way to see it. Suppose that sigma has outward orientation. So keep in mind that if sigma is the surface of a solid, it wraps around the solid. So there are only two possible orientations here. You can orient out through the surface or in through the surface. So then what the divergence theorem says is the surface integral of a vector field f dot n ds is equal to the triple integral over d of the divergence of f dv. So two notes. We'll do some examples. Two initial notes. There are a few notes that are going to come up. One is, again, D is the solid. Sigma is sort of the hollow, if you like, or is hollow. So, for example, if D were a cube, it would be a solid cube. So this is, for example, D is a solid cube. And in that case, sigma would be the hollow surface. One way you can think about it is if you take a D and you were to paint it, and then you were to make the object vanish, the paint would be the sigma. It would be the thing around the edge. So that's the first thing. And the second thing is how we do this final integral. The resulting integral, if you like, is up to D. Really, this is back to a triple integral, and you can do various options. You can do rectangular, cylindrical, spherical, for example. So let me do one example. I'll do a bunch of examples, but I'll do one simple one, and then I'll sort of do some more along with some notes that I want to make. So let's say examples and notes. So keep in mind, this is actually a really nice theorem because it takes a surface integral of a vector field, which is all sorts of convoluted. It's got i's and j's and k's. And when you take the divergence of it, you just get a scalar function. So you vanish out of having vectors and things to deal with like that and get down to something really, really nice. So let's say example, simple good first example. Let's say suppose that sigma is the cylinder. X squared plus y squared equals 4 between z equals 0 and z equals 5. And we have to say in this case, along with the disks, which seal the ends. So if you like, think something like a soup can. But not the soup, just the can. And the question is to evaluate the integral over sigma, and again, this will be oriented out. We'll evaluate the integral over sigma of x squared I plus 5yj plus 7zk dot n ds. So by the divergence theorem, this becomes a triple integral over d. And when we take the divergence, so it's been a little while since we took the divergence. So when we take the divergence of this vector field, we take the partial derivative of this guy. We used to call this m when we saw these. We take m's derivative with respect to x. We take n's derivative with respect to y. We take p's derivative with respect to z. We add those together. So what I get here is 2x plus 5 plus 7 dv. And just to be clear, this is where d is the solid cylinder. So I'll draw a picture here, just so we're clear. So there's d, it's filled in. Radius 2, height goes from 0 to 5. So d is solid. Sigma is sort of the can that surrounds it. So a good analogy might be that I said earlier, like think it's a soup can. So sigma is a soup can, and d is the soup. It's the thing inside the can. Now, at this point, we look at d. We go, hey, cylindrical coordinates. So when we parameterize this with cylindrical, we have theta on the outside, 0 to 2 pi. We have r next, which is 0 to 2. We have z, which is 0 to 5. We have 2x plus 12, but x is r cosine theta. And we have the polar r, dz, dr, d theta, and then we evaluate. So, again, this is really nice because it gets rid of all this stuff about having a vector field and a surface, which we might have to parameterize, and just shoots it right into like a nice triple integral that we can do in rectangular or cylindrical or spherical or whichever method we want to. So let me sort of do some other comments, do some other examples, make some notes. So let's say example / note. You could say something, if sigma is oriented inwards, this sort of should remind you a little bit of Green's theorem. So if sigma is oriented inwards, we could still use the divergence theorem, we just need to negate. Alright, so for example, to find the integral over sigma of, say, y plus xyj plus 3k dot n ds. Let's say sigma is a cube. I'll draw the cube rather than trying to describe it because it's sort of easier to draw than describe. Sort of tidy this up a bit. So I just want a cube sort of tucked into the first octant. So the cube here is hollow. Think of it like a cardboard box, but it's empty. And this will be oriented in. So by the divergence theorem, this becomes a negative integral over d. And again, the negative is there because we're oriented inwards. So this introduces this. We're sort of reversing the way we're thinking of things working. Then we take the divergence. So again, I go back up to this vector field. Take its divergence. So we take the partial of the first component with respect to x, that's 0. The second one with respect to y, that's x. The third one with respect to z, that's 0. And that's dv. And then in this case, and I didn't give dimensions for the cube. Let's say, I don't know, it's 7 units on a side. 7 by 7 by 7. So I can do X and Y and Z in any particular order because everything goes from 0 to 7. So let's do it in a sort of standard rectangular way. We'll put Z on the outside. And then, I don't know, X, Y, let's do Z, Y, X. And then here we just evaluate. That's actually pretty straightforward integral. So the key to see in this note is if sigma is oriented inwards, you simply negate. So next one is just a note, not an example. I guess I could put an example there as well. Say note example. So the note I want to make here is that sigma has to completely wrap around D or else this doesn't work. So completely surround D or else no dt, no divergence theorem. So for example, if sigma is a cylinder but not the ends, so you have a cylinder, but you can pass through it. In other words, it's not capped off. It's like a tin can, but you remove both ends. Then cannot use the divergence theorem here. So it has to be sort of capped off at both ends, or like if you had, for example, if sigma were a hemisphere. So think like a punch bowl, like this, but you can go inside it. It doesn't have a lid on top. Then no dt. If it had a lid, yes. So if the hemisphere had a lid, then it's okay. Because then it's surrounding a solid hemisphere, and then everything's good. That's a little note there, along with some pictorial examples. So, next example note. So if it turns out that the divergence of f is a constant, then look at what happens. Right? So we do this divergence theorem. We get the integral over d of a constant. Now, constants we can pull out, right? So this then becomes a constant times the integral over d of 1. The integral over d of 1 is just the volume of d. So we get the constant times the volume of d. So this is really, really useful if d happens to be a shape that you know the volume of, right? So this is great if we know the volume of d. If it's a cube, or a sphere, or a hemisphere, or a cylinder, or a cone, something basic, then we can use this. If it's something you don't know the volume of course, then you still have to do the integral because you have to figure it out. But so here's a really simple example. So, for example, sigma is the cone. Say z equals the square root of x squared plus y squared. So this is the cone opening upwards. I'll draw a picture in a second. Up to z equals 3. Along with the disk at the top. Pointed out. So in this case, if this were like this. This is our sigma. So it's not solid. It's like a paper cone, like a cone paper cup with a lid on top. Goes up to 3. So notice this is at a 45-degree angle, so the radius up here is also 3. And so then, suppose we wanted to, let's say, then find the integral over sigma of, say, 4xi plus 2xj plus, say, 3zk. Sorry, that have an extra integral sign there. Dot n ds. So by the divergence theorem, this becomes the triple integral over d, and then when I take the divergence, I get 4 plus 0 plus 3. So this is 7. So I can pull the 7 out, and we get 7 times the volume of the cone. Now, you may or may not know the volume of a cone, but it's a nice one to remember because it's really easy. So the volume of a cone is a third of a cylinder. So if you pretend this is a cylinder, it's got a height of, so the volume of a cylinder is pi r squared h. So this is 1/3 pi r squared h. And that's it. That's the answer. Done. Again, this only works because we know the volume of a cone. Right? If it were some other weird shape, we'd have to do the integral. There'd be no choice. On a final note, and this is sort of a somewhat technical note. You don't need to know this, right? So if these problems make sense, you can happily hit stop on the video now and call it a night or day or whatever time of day it is for you. It's night for me. So, but the note I want to make is just that this is one of the few theorems that we have that actually make sense. Now, all of the theorems that we've looked at make sense, right? Let's be clear. Even Stokes' theorem, it may be hard to sort of understand what's going on in terms of, say, fluid flow or magnetic fields or something, but they all have a meaning. But for most of them, in order to understand the meaning, you have to have a sort of a fairly good technical sense of what's going on physically. For the divergence theorem, you actually really don't. And so I can give you some insight as to why it is what it is, right? Or like why it makes sense. So consider what it says. Again, you don't need to know this. It's just sort of an interesting fact. Consider it says that this guy is integral over sigma, and remember sigma is oriented out. It's equal to this guy. So let's just remember what all these things are actually measuring, right? So what this guy over here is measuring, this is measuring the rate of flow of F, let's say outwards, because that's how sigma is oriented through sigma. Because remember that the surface integral of a vector field, we're thinking it as measuring the rate of flow of a fluid. Now, then we think, well, what does divergence measure? So this was way back in 15.1, so you might have to sort of ring a bell here. The divergence measures whether the fluid is sort of at each point, whether it's producing fluid or sort of sucking in fluid, whether the fluid is expanding or compressing. So this is this single thing right here. This is measuring at each point is the fluid being produced. If you prefer expanding, that's fine. Or being sort of vanished is maybe a good word. Right, like we have these terms like a source and a sink. If the divergence was positive, it's a source, it's producing fluid. If the divergence is negative, it's a sink. Fluid is vanishing at that point. But you can think about it as compressing. If you don't like your fluids to vanish, that's fine. And so when you do the integral, you actually add everything up. So what this whole thing is doing is saying overall in D, let's say, how is the fluid behaving? Is it, let's say, being produced or vanishing? Because when you do an integral, you sort of add all these notions up. It's sort of the meaning of an integral. So this kind of makes sense because if you think about it, if you have like a sphere, right? So Here's a picture that can help. I'll do it in green. If you had, say, a surface like sigma, and let's suppose that your fluid were, say, flowing like this, always out. So what happens is the fluid is being produced. So the divergence in this case is positive. And, well, if it produces fluid, where does the fluid go? Well, it has to cross the boundary. And that boundary is sigma. And that's why that integral is greater than 0. So again, this is it's very intuitive. It's not technical. I don't want to bring any units into it, but it just sort of gives you an understanding that on the left-hand side, you're measuring the flow across the surface. On the right-hand side, you're measuring what's happening to the fluid inside the object. And so clearly, if fluid is being produced inside the object, on the whole, it has to flow out across the boundary. And that's what the correspondence here is saying. And likewise, the reverse is, if on the whole, inside the object, the fluid is being vanished, being sucked in, it's like little sinks all over the place and it's going away, it has to come into the object from outside and it's crossing the boundary going inwards. So that's basically the meaning of the divergence theorem on the whole. It's a nice one because it kind of makes sense. And that is it. That is the end.